Hey, Professor Ampol, this is Braden Diver from the MAE 105A class, and I did an experiment over Mentos and Diet Coke. It's the classic experiment. You put the Mentos in the Diet Coke explodes. But I wanted to see, using thermodynamic principles, what the difference was if the Diet Coke was hot versus if it was cold. So I cooled some Diet Cokes down to about 41 degrees Fahrenheit. Then I put some out in the sun, and they got to around 88, 89 degrees Fahrenheit. And then I compared the two, and I saw what I got, and I used thermodynamic principles to explain why I get a change in height. All right, so let's get into it. Here we have the first equation. This is the first law of thermodynamics, the energy equation. We just have the change in internal energy over time, over change in time, equals Q dot minus W dot plus the sum of the energy from the mass going in minus sum of the energy from the mass going out. So really quick, I also have this diagram to the left side. This diagram shows what we're trying to calculate before going into this. So we see some Zi and Zj values. We'll get to that. But pretty much I define Z2 as equal to Zj at the top, and Z1 is equal to Zi at the bottom. And so we have a delta Z equal to Z2 minus Z1. And so I had to multiply it by the change in time, because this is a flow formula. And all I had was, I didn't have a constant flow, I just had a one-time flow. And the way I set the mass up is I define mass to be the total mass. So I'm going to prove that for the total internal mass energy for the Diet Coke. And I'm making the assumption that the total mass of the Diet Coke ends up at this altitude, which I know is not true, but using the formula, we'll be able to, using the formula like that, we'll still be able to prove that the change in height, if we were taking the total mass, would still be greater than the change in height for the total mass of a lower temperature system. So we're gonna look at this. So we have delta U of the control volume equals just Q minus W plus the mass flowing in minus mass flowing out times the variables there. All we did was multiply m dot times time to get m. And we have some assumptions here. So an adiabatic process, which means our Q goes to 0. And it also means that we're also not having a change in mass from one spot to the other. No work done. W equals 0 because we're also assuming an inviscid flow, which means no friction from here to here. Ideally, there'd be air resistance in this formula, but that's a bit too advanced, and it's actually the same for both the high and low temperature, so I didn't figure I needed that in my equation. And we also are going to assume that the Diet Coke is incompressible, which since it's a liquid, it's incompressible, and we will get to using that a bit later on. We're going to assume that the velocity at I, which we're defining I, we're saying that VI is equal to the velocity at 1 at the bottom equals Vj equals 0. So we're going from a system where it's contained in the container, if we could have the Mentos with the Diet Coke in the container together, versus a system after you unscrew it, and we assume that all of the mass is up here at the top of the palm tree looking, it's supposed to be the liquid, the palm tree looking liquid up top. And first we're going to apply the change in mass of the control volume over the change in time equal to the sum of the mass rate going in minus the sum of the mass rates going out. And this goes to 0 because we're assuming it's the whole mass, of course. So m dot I equals m dot J, and if we multiply that by time again, which we're going to do, we get mi equals mj, which we're just going to call m. And then we can take this formula up top that we derived from our King formula at the very top to get, here we have the change in internal energy equals mass times the enthalpy initial plus gravity times the initial height minus the final enthalpy minus gravity times the final height. And if we substitute m times u2 minus u1 in there, we get this equation, which is just u, the lowercase u. This is an easy substitution we learned about a lot. And here I'm defining some things, just that our initial values are equal to h1. So hi is h1, hj is h2, and then zi is z1, zj is z2. So we have u2 minus u1 equals h1 plus gz1 minus h2 minus gz2. We just divide the masses out, and we're going to solve for delta z, because delta z is the height, and that's what we want to end up comparing at the very end. So here we're going to group together the z's by putting it in a parentheses right next to gravity, and we're going to multiply it all by -1 because we want the delta z, which is z2 minus z1, not z1 minus z2. And now we're going to get to delta z. Delta z equals z2 minus z1, which, deriving from those equations, is equal to u1 plus h1 minus the quantity u2 plus h2, all of that divided by gravity. And simply using h, our enthalpy, equals u, our internal energy per mass, plus pressure times specific volume into that equation, we get delta z equals u1 from there, plus u1 plus p1 v1 from there, minus u2 from there, minus u2 again from there, minus p2 v2 from there as well, divided by gravity still. And delta z, we assume that our specific volume v1 equals v2 equals, we're going to call it v sub coke, because at the beginning we assume Diet Coke is incompressible, which would mean the specific volume is the same. And then here we have the factor 2 in front, just adding those together. Experimentally, we're going to find that our P1 is greater than our P2. So this makes sense. This shows that if our P1 was less than P2, it would be possible to get a negative delta Z value, but experimentally, we know that our delta Z is positive, and if P1 was less than P2, the delta Z would end up being negative. So we're gonna go with that. It's pretty much an assumption, but it's an assumption based on experiment. And now we want to prove that our delta Z of the hot is greater than delta Z of the low. So we're gonna start by writing the equations with subscripts for both as required and multiplying out the G because that's a constant between the two. So we have 2 times the internal energy at 0.1 when it's hot minus internal energy at 0.2 when it's hot plus specific volume times the pressure at 1 when it's hot minus pressure of 2 when it's hot, and that's greater than 2 times U, the internal energy of 1 when it's low, minus U, the internal energy at 2 when it's low, plus the specific volume times pressure 1 while it's low minus pressure of 2 while it's low. So first we have we're going to split it into 2, make it a bit easier on ourselves. So if we prove first that V coke times P1H minus P2H is greater than V coke P1 low minus P2 low, and then we prove 2 times U1H minus U2H is greater than 2 times U1L minus U2L, then this statement is true, which means that this statement is true as well, which means that delta Z hot is greater than delta Z low. So first we prove the second. We're gonna show that the specific volume of Coke times P1 at hot minus P2 at hot is greater than V Coke times P1 at low minus P2 at low. Well, we know that the P2 values are equal to the pressure at atmosphere, and that's because this is P1, this is P2. It's going to be equal to the pressure, or roughly equal to the pressure of the atmosphere outside, based on our principles on fluids there. So this simplifies to, we divide out V Coke and assume those are similar and subtract those out. So P1 hot is greater than P2 hot. We use PV equals RT to use RT hot over V. The specific volume is greater than RT low over V, the specific volume again. The V's are the same because incompressible, and we get T hot is greater than T low, which is true based on our definition of T hot and T low. Now, our last thing to prove over here is that 2 times the internal energy at 1 while it's hot minus U, the internal energy at 2 hot, is greater than 2 times the internal energy at 1 low minus U, the internal energy at 2 while it's low. So our U1H minus U2H is greater than U1L minus U2L. And first, to evaluate this, we will look and see that U is a function of pressure and temperature. You can look at the charts in the back of the book, and you'll notice obviously that the higher the temperature and the higher the pressure, the greater the value of U. So then we look at the change in temperatures to see the change in temperatures between the two values. Well, since the change in temperatures of the two values is the same, then the U's are going to be the same in that regard, right? But then we look at the change in the pressures. Well, the change in the pressure for H is going to be higher than the change in pressure of L, which means that which is based on this fact over here that we already derived, because the U sub 2's are at atmospheric pressures, and the U sub 1 here is at a higher temperature, which means a higher pressure, and that U sub 1 L is at a lower temperature, lower temperature, which means a lower pressure. And although they're both at the same temperature, that difference in pressure is what causes the difference in internal energy, and that proves that statement as well, which proves this statement. And we have fully proved that our change in Z, or height, for a hot should be greater than our change in Z for the lower temperature. So here we have proven that using the principles of thermodynamics, that a higher temperature Diet Coke with Mentos results in a higher explosion. Thank you very much for your time. All right, Professor, now it's the moment you've been waiting for. We have the experiments. I'm gonna just put them back to back to back to back to back with very little editing. But first we're gonna go through the first 3, which are going to be the lower temperature, and the lower temperature is at 41 degrees Fahrenheit. And then we're gonna have 3 at the higher temperature. The third of the higher temperature is actually, it didn't go off too well because I kind of missed some of the Mentos, so kind of use that one as an error if you see that it gets quite a bit lower than the first 2 at the high temperature. But I used the same amount of Mentos going into the soda for the other 5. There we go. That was a good one. All of it went out.